In this video, I'm going to show you how to use the first derivative test to classify local extrema. Here we want to find the relative maximum and relative minimum points of the function f of x equals 1/3 x cubed plus x squared minus 3x. And here's our game plan. First, we will find the critical points, since these are the only values that could possibly be maxima or minima. Then, once we've found those critical points, we'll figure out where the function is increasing or decreasing and use that information to determine whether each critical point is a maximum or a minimum. Okay, so first task, find the critical points. Critical points are where the derivative is 0 or undefined, so first of all we have to compute the derivative. The derivative, f prime of x, is given by derivative of 1/3 x cubed. That becomes 1/3 times 3x squared, which becomes just x squared. And then plus derivative of x squared, which is 2x, and then minus derivative of 3x, which is minus 3. Now the derivative is a polynomial, so of course it's defined everywhere, so we just need to figure out where is the derivative equal to 0. Those will give us the only critical points. So 0 equals x squared plus 2x minus 3, and we can solve this equation by factoring. This quadratic factors very nicely. Factors into x plus 3 times x minus 1. So the solutions there are the roots of the factors, so x equals -3 and 1. These critical points split our number line into 3 subintervals. Why don't we actually draw this out so that you can see? So here's our number line. Just draw a straight line across, and let's go ahead and plot our critical points on there. We'll have -3 over here, and 1 over here. So the 3 intervals then are this one over here from -infinity all the way to -3, then the interval between these two critical points from -3 to 1, and then the interval from 1 onwards, so 1 to infinity. Now we need to tell, is the function increasing or decreasing on each one of these intervals? And the way we can do this is we can choose test points within the intervals to test the sign of the derivative. Whatever result we get for the derivative at the test point will hold for all the values of x in an entire interval. And why don't we make a table to organize our work? In this table we'll keep track of x, the derivative, f prime of x, and we'll also include what that says about the actual function, whether it's increasing or decreasing. Now there's 3 more columns corresponding to the 3 intervals, -infinity, -3, -3, 1, and 1, infinity. Now let's go through and choose test points. In the first interval, from -infinity to -3, how about a test point of -4? Since f prime of x is equal to x plus 3 times x minus 1, as we saw when we factored, we know that f prime of -4 is equal to -4 plus 3, which is -1, times -4 minus 1, which is -5. This is equal to 5, which is obviously greater than 0. So that means, on this entire interval from -infinity to -3, the derivative f prime of x is positive. And that means the function f then is increasing. It's going upwards. Okay, now to just repeat this process for the other 2 intervals. On -3, 1, we've got an easy test point of 0, and we'll check the derivative, f prime of 0, is equal to 0 plus 3, which is 3, times 0 minus 1, which is -1, which is equal to -3, which is less than 0. So derivative is negative, and the function, therefore, is decreasing. On the final interval, from 1 to infinity, how about let's choose a test point of 2. Then we have f prime of 2 is equal to 2 plus 3, which is 5, times 2 minus 1, which is 1, which is 5, which is greater than 0. So derivative is positive, and the function is increasing. So our function f of x looks something like this. It's increasing up until x equals -3, and then it's decreasing up until x equals 1, and then it's increasing again. So we see that x equals -3 is a maximum, while x equals 1 is a minimum. So we can write down our final answer. Relative maximum is x equals -3, and relative minimum is x equals 1. And here we go. We're done. We've got it. Now, this procedure that we just did is called the first derivative test. We first figure out the critical points of the function, and then we figure out where the function is increasing or decreasing, and then we infer whether each critical point is a max or a min. If the derivative switches from positive to negative, then it's a maximum, whereas if the derivative switches from negative to positive, it's a minimum. And you can always draw a little sketch of the function to visualize what's going on. Here's the next problem. We want to find the relative maximum and relative minimum points of the function f of x equals x minus 2 cubed using the first derivative test. So, as usual, we're going to differentiate the function first because we want to find the critical points. F prime of x is equal to 3 times x minus 2 squared, and then the chain rule on the inside would just give us a derivative of 1. If we multiply by 1, it stays the same, so this is the full derivative. Now, this is defined everywhere, so the critical points will just happen where the derivative is equal to 0. So 0 equals 3 times x minus 2 squared, and the only factor here is x minus 2, so the only 0 is going to be x equals 2. Let's draw up our number line here. X equals 2 breaks up our number line into two subintervals. There's one subinterval to the left of 2, which goes from -infinity to 2, and then there's another to the right of 2, which goes from 2 to infinity. To check the sign of the derivative on each one of these subintervals, we're going to use some test points, so let's draw up a table. First of all, let's get a test point in the interval from -infinity to 2. So how about 0? 0 is usually the easiest test point if you can get it. So let's check. F prime of 0 is equal to 3 times 0 minus 2, which is -2, squared, which is 3 times 4, which is 12, which is greater than 0. So derivative is positive for all values of x inside of this interval, and so the function is increasing over that entire interval. We'll do the same thing with the next interval from 2 to positive infinity. Let's just choose a test point, how about 3? And we see that f prime of 3 is equal to 3 times 3 minus 2, which is 1, squared, which is just 3. That's also greater than 0. So derivative is still positive here, and function is still increasing here. So if we draw a little sketch of our function, the function is increasing until it gets to x equals 2, and it kind of levels off because its derivative is 0 at x equals 2, but then it continues increasing afterwards. So we see that this critical point, x equals 2, is neither a max nor a min. There are lower values to the left of it, but higher values to the right of it. The function is just flat at that area, but it doesn't form a peak nor a valley. We call it a saddle point. But the overall conclusion from the first derivative test here is that there are no relative maxima nor minima. And that's it. Just nothing. That's our final result. Here's the next problem. We want to find the relative maximum and relative minimum points of the function f of x, which is defined for all x not equal to 2 and whose derivative is given by f prime of x equals x squared times x minus 3 all over x plus 2. And to do this, we're going to use the same process as before, the first derivative test. We'll first find the critical points, and then find the intervals on which the function is increasing or decreasing, and then we'll classify those critical points. This time, we have the derivative given to us. The critical points are where the derivative is 0 or undefined. And we know that if f prime of x is equal to 0, then the numerator has to be 0, and that would correspond to roots of factors of the numerator. The root of x squared is just 0, and the root of x minus 3 is just 3. So those are the critical points arising from the derivative being equal to 0. But we can also get critical points from the derivative being undefined. And the derivative is undefined where the denominator is equal to 0. So the root of the denominator is x equals -2. Now, if you remember the precise definition of critical points, you'll realize that x equals -2 is not actually a critical point. And the reason for that is because the function f is not defined at x equals -2. The point's not even in the domain of the actual function f. And we're told that right over here. F is defined for all x not equal to -2. So although this is true, it's still possible that the derivative could change sign from the left of -2 to the right of -2. So we still need to include it in our calculations, even though it can't actually be a max or a min. So we still need to include it in our calculations, even though it can't be a max or a min itself. So let's go ahead and proceed as usual, splitting up the number line. Here's our number line. Here's our points at -2, 0, and 3. We've got 4 intervals. One interval from -infinity to -2, another interval from -2 to 0, another interval from 0 to 3, and one last interval from 3 to infinity. And we'll go ahead and make a table to organize our results. Let's go ahead and run the process on our first interval. Choose a test point between -infinity and -2. How about -3? Find out the derivative value there. Is it positive or negative? Let's compute. F prime of -3 is equal to -3 squared, which is 9, times -3 minus 3, which is -6, all over -3 plus 2, which is -1. And that makes -54 over -1, which is positive 54. And that's greater than 0. So the derivative is positive everywhere in this interval, and the function is then increasing. On to the next interval. How about a test point of -1? We'll evaluate the derivative. F prime of -1 is equal to -1 squared, which is 1, times -1 minus 3, which is -4, all over -1 plus 2, which is 1. This comes out to -4, and that's less than 0. So derivative is negative, function is decreasing. Another test point in 0, 3, how about +1? So we'll compute f prime of +1 is equal to 1 squared, which is just 1, times 1 minus 3, which is -2, times 1 plus 2, which is 3. This is equal to -2/3, which is less than 0. So derivative is negative, function is decreasing. And then lastly, in the interval from 3 to infinity, how about a test point of 4? We know that f prime of 4 is equal to 4 squared, which is 16, then times 4 minus 3, which is 1, then all over 4 plus 2, which is 6. That comes out to 16 over 6, and we could simplify this a bit more, but it really doesn't matter because we know it's positive. So that's greater than 0. Derivative is positive, function is increasing. So looking at our table, we see the function is increasing until -2, and then it's decreasing afterward. And that looks like we have a relative max at x equals -2. The function continues decreasing until x is 0, but then it's decreasing afterwards as well, so there's no max or min there, that's just a saddle point. but then it stops decreasing at x equals 3 and it starts increasing. So that's a relative min at x equals 3. But wait a second, something's wrong here. Remember what we said initially about x equals -2? It's actually not a critical point because the function is not defined at x equals -2. We still needed to include it into our calculations, but it can't be a max or a min itself because the function is not actually defined there. So we actually don't have a relative max at x equals -2. Maybe the function has a hole there, or an asymptote, or something like that. Either way, the function is not defined there, so it cannot be a maximum of the function. All we have for our final answer is a relative minimum at x equals 3. And there we go. That's it. Now we know how to use the first derivative test to classify local extrema. In the future, we'll learn another way to classify local extrema using the second derivative test. And we'll also see how to find not just local extrema, but also global extrema.